Hello guys, my name is Gyanvi Singh. Today I am going to present the topic that is type of flip-flops and their conversions. It is presented by Gyanvi Singh. So before starting our topic of flip-flop, we have to understand about the basics of flip-flop, what were the basic design and what was the root of the flip-flop, from where they evolved and from where they came from. So let me move to the next slide. This is a sequential circuit. This diagram is represent a sequential circuit, but sequential circuit consists combinational logic circuit and memory. We have to understand combinational logic circuit first, then we would be able to understand the sequential circuit. So combinational logic circuit, the circuit whose output, this is my output, is depend on present input. Okay, so combinational logic circuit is a circuit whose present output is depend on present input, and sequential circuit consists combinational logic circuit as well the memory element connected in the fashion of feedback, in the form of feedback. Okay, this is connected in the feedback form. So sequential circuit output is depend on present input as well as past output. This input is coming from the past output through a memory element and connected in the form of feedback. Okay, so we would be able to understand about the memory first of all. Let me discuss about the memory. So a memory unit is the circuit which is connected in the cascade form. I have two inverters and these two inverters are connected in the cascade form. As you can see, the output of this NOT gate is connected as an input of this NOT gate, and the output of this NOT gate is connected as an input of this gate. So suppose I am trying to fed 1 here, the output will be 0 and 0 will be coming as a 1 through the output of NOT gate, and as you can see I am able to store a 1 bit. Here I am getting 1, here I am getting 0. Okay, so this is a basic idea of making a memory. How we developed a memory, this is the basic of memory. How we are able to store a 1 bit. So this is the reason how we can store or save 1 bit. Okay, so 1 bit memory cell. And the issue was that in this circuit, as you can see, I don't have any controllability. I mean, how would I be able to fed the input? You can see here that there is no terminal, there is no input terminal through which terminal I should put 1, 0. So I just modified this circuit. For that, what I did, I just replaced this NOT gate with a NOR gate. This is my NOR gate. Okay, so the NOR gate functionality is, it is just when 0, 0 I will provide, it will give 1. When I will give 0, 1, it will give 0. When I will give 1, 0, it will provide 0. If I put 1, 1, it will provide 0. Alright, so what I did, I just replaced NOT gate with the NOR gate so that I should control or give the input through one terminal. So when I make this A terminal 0 and whatever I will give through this terminal, I will get the complement of B bar. Okay, the functionality of this NOR gate is equivalent to this NOT gate. As you can through the truth table also, if I make 0, 0, here this A terminal I have made 0. Now the other terminal is 0, it will give 1. Other terminal is 1, it will give 0. Okay, now you can observe it is working similarly as a NOT gate. Next slide. What I did, I had a cascade form of NOT gate which was connected back to back. I just replaced this NOT gate with a NOR gate. This is my NOR gate. Okay, I have replaced it with. Now I have a controllability of this terminal. I can fed the input whatever I want. Alright, so I have mentioned here memory unit with NOR gate, replace with the NOT gate. Now I just took that same circuit, I replaced the fashion. I just changed the fashion. Here you can see NOR gate was connected here and here. Now I just change the fashion. The diagram is same, but I just put this NOR gate below. The diagram is same. Now this diagram is equivalent to that previous diagram where these two NOR gate are connected in the cross coupled form. I have a two terminal where I can put the input. So I have placed the name R or S. What do you mean R and S? R means reset, S means set. And on the basis of the input combinations, I would be able to get the output Q and Q bar. This circuit name is latch. This is our latch. Okay, the name latch itself says that it is able to store the or latch the 1 bit of memory. So latch is nothing but a 1-bit memory cell which is capable of retaining the past state of output. Alright. So RS latch, and this is the truth table. I have written some combination and corresponding output and what output they will represent. So I have represent these output with a state name that is set. Okay, no change, reset, no change. Let's understand one by one. So when I will give 0 or 1, I will get 1 0. This state is called set. Why it is set? Here you can see S. I'm providing 1 to the S terminal. I'm getting 1 at Q terminal. So it is set the state. Okay. Now if I give 0 0, what it will do? 0 0 is just retain that previous state. It means it will not change the state. It will keep that previous state. So no change. The state name is called no change. Now I give 1 0. So 1 I am providing to the R terminal. It means reset. It will make this Q reset. So what it will get? 0. Reset means 0. Okay. Now 0 0 again I provide. Just to check and just to see what will do the output. I am getting 0 and 1. So no change again. Okay. Then I will give 1 1. This 1 1 is invalid state because it is providing 0 0, and you know Q and Q bar is never equivalent to 0 0, means these both output are complement to each other, but I am getting the same value. So this is an invalid state. Again I give 0 0, then what it will do? 0 0 will be replaced to the 1 1. Previous state was our 0 0. Now it will change to 1 1. Again 0 0, then 1 1. In that case it will be continuously a race around condition. It will never stop. Okay. Let's move to next slide. SR latch using NAND gate. So what I did, I just try to replace those NOR gate with NAND gate. So I just replaced this NOR gate with a NAND gate. This is my same diagram as previous. Okay. So here you can see, but they are working. Just some modification I had done. See here you can see, if I provide 1 1, I will get 0 0. But previously in the NOR gate, when I was giving 0 0 here, I was getting no change. Right? Here you can see 0 0 I am giving, I am getting no change, 1 0 state. But here I am giving 1 1, I am getting no change. Okay. But the circuit is working, but in the complement fashion. 1 0 I am giving, I am getting 3 0 1 reset. Means if I am giving 1 to the S, then it will reset. If I am giving 1 to the R, it is set, and again I am 0 0 invalid. Here the invalid state was when I was giving 1 1. Okay. So just to make this circuit equivalent to the previous RS latch made by NOR gate, what I did, I just put NAND gate just before of this SR latch made up of NAND gate. Now see the result. If I'm giving here, if I'm giving 0 0 no change, 0 1 reset, 1 0 set, and 1 1 invalid. Now this circuit is working perfectly as equivalent to this RS latch with NOR gate. Okay. So somebody can ask why we use NAND gate. This is another topic. I will explain later about it, because if I do explanation of this NAND gate or NOR gate, then the video will become long. So just I will make some another video for that concept. Okay, now what I did, I just joined R and S together with the NOT gate. Here I am showing you NOT gate I have connected, and connected the SR terminal together. Okay, so this latch is working as a gated D latch, and this is called gated D latch. Why? Because if I make enable 1, now my latch will be enable, and whatever I will give 0, whatever I will give here, it will reflect the same value here at Q. That's why we called D latch also the transparent latch. Okay, whatever I will give, it will reflect here. For example, if I'm giving 0, it will provide 0 here. If I'm giving 1, it will provide 1 here. Okay, now, so up to here, this was the latch. Now we will understand how the D flip-flop we made from the latch. So I just connected, suppose I am trying to make a D flip-flop. This is a diagram of D flip-flop, negative edge trigger D flip-flop. So this is my master D latch and this is my slave D latch. Okay, so what I did, I just connected a master D latch or slave D latch in this fashion, and enable signal I connected means this is a synchronous circuit where the NOT gate I have connected. I'm providing a negative label triggered to the slave D latch. Okay, whatever the output it will come here, it will work as an input for this slave D latch. So you can also do the practice, and also you can see by practical by drawing a waveform how the output will be appeared at Q terminal. So, and that output of this Q terminal, suppose you make a 4 cycles, okay, and provide some D input, and see what will be the output here. This terminal, what will be the output by providing a positive label triggered, and that output will be work as an input for this slave D latch, and check what is the output here. Okay, and for that same D input, just draw the waveform of negative edge triggered. Suppose I negative edge, at the negative edge, what will be the output? Means negative edge triggered D flip-flop and made a waveform. Okay, then you will realize that the output here and the negative edge triggered D flip-flop output waveform will be matched together, will be equivalent to each other. So you will see, yes, that will confirm, yes, this is the D flip-flop which is made up of D latch. Okay, let's move to the next slide. So same scenario, in the same fashion, I made SR flip-flop where I connected that Q and Q bar to the S or R. Okay, same diagram, right? So this is the truth table of SR flip-flop. 0 0, I will get no change. If I give 0 0 here, I will get no change. Whatever the previous input, I will get the same, it will keep the same. If I give 0 0, it will retain the same output. Okay, then if I give 0 1 here, it will reset. Why reset? Because 1 is on, we are giving to the R terminal, it will make this terminal reset. If I give 1 0, it will set. If I give 1 1, it will invalid state. Invalid state means this equal to this will be equal to 1, and it will never equivalent to each other, right? This is an invalid state. Just to remove this state, we came across the JK flip-flop. So JK flip-flop is a modification of a SR flip-flop to just remove this invalid state. So this is the waveform, and this waveform is the explanation of how this output is showing. And when I give clock, this is my clock, and this is S or R. So you can see here 0 or 1, I'm giving 0 or 1 here, I'm getting output 0. Till next edge I will get 0. Here 1 or 0, I'm getting set. Till next edge, set means 1. Again 0 1, then reset, then it will become reset up to next edge, then 0 0, it will keep the state same, then 0 1, then again it will reset, then I'm getting 1 0, then it will set, then 0 0, it will keep the state same, then again 0 0 till the next touch it will be same. And this is the excitation table. Excitation table represent the combination of input which will provide the particular output. This is my some combination of input, and corresponding to that this is the output which I will get. Okay, so excitation table just represent what input I will give and corresponding what output I will get. That is called excitation table. This is the same thing which I draw for the D flip-flop. This is the truth table and this is the waveform. The waveform, as you can see, at the positive label triggered, when it will be positive label triggered, positive edge triggered, when it will be positive edge triggered, if I provide 0, it will provide 0 till next edge. It is 1 till next edge it will 1, then again 0 till next edge 0, 0 again till next edge it will 0, and then it is 1, then next it will move till next edge 1. I am getting 0, I am providing 0, then I will get 0 till next edge. In that fashion, the waveform will continuous. Same excitation table of the D flip-flop. Okay. Now, JK flip-flop, I told you JK flip-flop is the modification of the SR flip-flop. So the truth table is same, but in the 1 1 when I will give, it will toggle. Toggle means once it will be 0 or 1, then it will be 1 or 0. It means it will, in the next cycle, it will toggle. Means when 1 1 state I will provide, then the output will be toggle. Actually, toggled or race around, there is a big difference between them. Toggle means it is a controlling state. It is under controlled. But race around is uncontrolled state. It will definitely within a one time period, a number of output will be continuously changing between the time period. But toggle means the output change only once in a one time period. Okay, so for example, I am providing the clock here and J or K. Suppose 0 or K, I am feeding 0 0. The output I will get what? So there's no change, right? Previously, the output were I considered here 0. This is the 0 and I'm getting 0 here. Now here I am providing this is 1 or 0. So when I will provide 1 or 0, I will get 1. So here I am getting 1. Again 1 0. Then again what will happen? It will goes to the 0. Why? Because J is 1. Okay, and K is 1. K is also 1, so it will toggle. Here you can see previously it was 1, now it toggle 0. Then again 1 1, again it moved from 0 to 1, it is toggle. Then again 0 0, it will keep the state same. Then 0 or 1. So what it will do? It is 0 here and here 0. At this edge 0 0, it means it will keep the state same till next edge. Here it is 1 and 1, it will toggle. Okay, and 1 and 1, it is toggle. Again it will toggle. In that way, it will be continuously move. Okay, this is a T flip-flop. So T flip-flop we made by connecting this J or K together. We will get T flip-flop. Okay, so how the T flip-flop work? When I make T equal to 1, the output will be toggle. That's why we always prefer JK or T just to draw or to make a counters. Okay, so we can see the waveform. For example, I am providing 0 here. At this edge, it will, suppose that the output is 0, right? It will get, if I am providing 0 here, then at this edge, no change I will get. Okay, no change till next edge. If I am providing 1, whenever I provide 1, it will toggle. So here 0 to 1, it will move. Again I am providing 1, 1 to 0, 0, no change, 0, no change. At 1, it will toggle continuously. Then here again it will toggle. Okay, in that way it will be moved. Excitation same. Now I have drawn a summary of excitation table. Here it is just for the easiness, I have drawn the excitation table to understand the combinations easily. Alright, now conversions of flip-flop. Till here I hope you understand about the different type of flip-flop and how they were made and how they were evolved, right, and what kind of the different type of the flip-flop we made. Now we move to the conversion of flip-flop. Conversions of flip-flop means that from one flip-flop we are able to convert to other flip-flop. Okay, so to convert the one flip-flop to other, there are some steps we have to follow. Those steps I have mentioned here. So consider the characteristic table of desired flip-flop. For example, I want to convert a SR flip-flop to JK flip-flop. Okay, so JK flip-flop, I will take the characteristic table of JK flip-flop and the excitation table of SR flip-flop. Now fill the excitation value input of given flip-flop. I have a given flip-flop of what? SR flip-flop I have a given. So I will fill the excitation values input of a given flip-flop for each combination of present state and next state. Okay, and on the basis of those combinations, I will just simplify the expression for the corresponding S or R. Okay, and we can use the K-map for simplified the expressions, right? Then we will draw the circuit diagram of the desired flip-flop according to the simplified expression using given flip-flop and necessary logic gates. Let me take some example to understand it very clearly. So I have taken the example of SR flip-flop to JK flip-flop conversions. Now this excitation table, see J, K, Qn, Qn plus 1. I just want to draw the JK flip-flop from SR flip-flop. They have given SR flip-flop. Okay, the excitation table for conversions of SR flip-flop into JK flip-flop is given below. So what I will do, I will just draw the characteristic table of a JK flip-flop, and based on this output combination, I will write the input here. Okay, what input I will fill here so that I get this output. So 0 at X we will get 0 0, X and 0 I will get 1 1, 0x I will get 0 0, 0 1 I will get 1 0 0. In that way I will fill these all S or R column. Then we will draw the logic expressions, okay, of S and the logic expression for R also. Now by using the K-map, I will simplify the logic expression and will write S equal to JQN bar or R equal to KQN. On the basis of these expressions, I have a SR flip-flop and I will draw the output. Here you can say the S is connected through AND gate J and output of Q complement. Okay, and this AND gate input is K and QN bar. Sorry, QN. So QN we will get from here, and through this AND gate the output is connected to the R terminal of SR flip-flop. In that way we will get the JK flip-flop. This is the final diagram of JK flip-flop. In that way we will be able to draw the JK flip-flop from SR flip-flop. Okay, now other conversions in the flip-flop circuit I have written here, and for the practice you can draw your own waveform, own diagram, and try to find out the logic expressions from and try to convert the flip-flop from one to another. Because of the saving of the time, I just give the one example. Rest of the examples I have draw the output, what will be the combination and what will be the terminal name and how they will be connected, I have written here, and for the cross confirmation you can refer this table. So this would be the final video. Okay, I hope you understand and you would be able to convert the flip-flop from one to another. I hope you enjoy this session. Thank you so much.